Welcome back to a new episode of One Wingspan Above, where we discuss anything to do with Ground Effect. My name is Paul Dutch. This episode is packed with all sorts of surface skimming craziness, so let's get started. We begin in a cold shed in the UK with James Walmsley. James set out to prove a point that many aeronautical engineers have debated for decades. That Ground Effect isn't just a playground for military superpowers. It's a physical reality accessible to anyone with enough insulation board, epoxy and sheer grit. At a massive 4-meter wingspan, his RC craft was designed to be a technical titan. But as he moved from the drawing board to rugged lake, he slammed headfirst into the transition gap. Building a wig craft is fundamentally harder than building a plane or a boat, because you have to build both at the same time. This craft featured a high lift airframe, but at over 20 kilograms, it's at heavy in the water. This triggered the dreaded suction problem. In hydrodynamics, a flat-bottomed surface moving across water creates a vacuum. If you don't physically break the surface tension, no amount of propeller thrust will ever get you airborne. You'll just have to be a very fast, very inefficient boat. Watch the engineering desperate measure here. To get the Titan onto the step, James had to think like a 1950s naval architect. He added a physical step in the hull, but the original wasn't deep enough to aerate the bottom. His fix? Plastic skirting boards. By screwing these into the hull, he created a sharp break that allowed air to bleed under the craft as it gained speed. This aeration is the aha moment of ground effect engineering. It snaps the water's grip, allowing the transition from a high drag displacement vessel to a high speed planing craft. But the aeration was only half the battle. The trailing edge of the wing was still sticking to the water as it sat too low. James countered this with a technical hack based on a suggestion from his crew. He cut part of the wing's trailing edge, physically moving it away from the water. Finally, the moment of truth. James pushed the throttle forward and those 4 motors screamed to an estimated combined 10 kilograms of thrust. At first the physics seemed to be winning. The craft labored, pushing a massive bow wave and dragging a heavy spray-filled wake. For several seconds it looked like the foam Titan was going to stay a boat forever. And then the breakout. As the speed hit the critical threshold, the skirting boards did their job. Air rushed under the hull, the vacuum snapped like a dry twig, and the Titan pops onto the step. Suddenly the drag fell off a cliff. The bow dropped, the spray settled into 2 razor-thin lines, and the craft accelerated with a terrifying surge. Then the magic happened. The craft lifted, not by feet, but by inches. It locked into the 1 wingspan zone. For the next 40 seconds, we saw a masterclass in boundary layer flight. The Titan looked ghostly, almost physically tethered to the lake. Because the induced drag was crushed by the ground effect, the efficiency was staggering. You could actually see the craft gaining speed while James held the power constant. James was working the elevator sticks with the precision of a surgeon. At this altitude, there is zero margin for error. As he pulled up too high, he'd leave the high pressure cushion, lose that extra lift and stall. If he dipped the nose by even a single degree, the 20-kilogram monster would become a high-speed torpedo. But he held the balance. For nearly a minute, the Titan skimmed the surface, its shadow racing perfectly beneath it on a self-generated piston of air. It was a hauntingly beautiful sight. A do-it-yourself shed build behaving exactly like the Soviet KN of 1966. James proved that the sweet spot isn't just a military secret. It's a physical playground for anyone brave enough to balance on a cushion of air just 1 wingspan above the deep. While James was proving the physics with foam boards in a UK shed, Across the Atlantic, creator Matt Spears was uncovering a literal ghost. Deep in a Wisconsin barn, buried under 30 years of dust, sat a machine, a US Navy Ground Effect prototype. It isn't a hobbyist build, this is a technical relic of 1980s military obsession, representing the American response to the massive Soviet iconoclasts. To understand the DNA of this craft, we have to look at the American winged hovercraft movement. While the Soviets were building massive rigid hull monsters, American innovators like Universal Hovercraft were pioneering a more versatile hybrid. Universal Hovercraft's Hoverwing series, specifically the UH-18W, became the gold standards for this technology. They proved that you could take a traditional hovercraft hull, add a set of broad wings, and use the air cushion to pop the craft out of the water's drag completely. The hoverwing concept was revolutionary because it allowed a vehicle to operate as a standard hovercraft over mud and ice, but once you hit 70 km an hour, it would lift off the surface and fly in pure ground effect. The Navy prototype Matt found is essentially the militarized big brother of that universal hovercraft philosophy. A rugged, supercharged beast designed to take the hoverwing's versatility and scale it for high-speed coastal reconnaissance. The Navy Beast is propelled by a supercharged 2.0-liter Chevy Ecotec engine, a choice that reflects a very specific era of American engineering, putting out a solid 200 horsepower, but it's the airflow that is truly the technical masterpiece. This craft utilizes a static air cushion. Unlike a standard plane that relies on a long runway to gain enough forward speed to generate lift, a hovercraft uses its front-mounted fan to blast high-velocity air directly into a heavy-duty hovercraft-style skirt. This creates static lift, and the craft can literally pop out of the water while sitting perfectly still. And to gain speed, that hover air transitions into aerodynamic lift under the wings. In its prime, it was designed to cruise effortlessly above the surface, but it possessed a jump capability that allowed the pilot to pull it up to clear obstacles. It was essentially the most advanced all-terrain hybrid vehicle of the day. But the years haven't been kind to this military secret. Now that Matt has it in a shop, the technical reality is a nightmare. Like many of his designs inspired by the Universal Hovercraft era, this craft is a composite sandwich, a foam core covered in plywood, wrapped in a fiberglass skin. Because it's sat outside in the Wisconsin elements for years, water seeped past the fiberglass, turning the internal structure into a sponge. Matt discovered that the engine mounts, the structural heart of the machine, were completely rotted away, looking more like black mulch than structural timber. If he tried to fire up that supercharged Chevy, the massive engine torque likely would have ripped the entire mounting structure clean out of the rotten hull. And the problems weren't just mechanical, they were biological. The craft had become a literal ecosystem. Matt found entire colonies of carpenter ants that hollowed out the saturated foam, hollowing out the structural integrity of the wing roots. While Matt Spears is fighting a biological war against ants to save a piece of history, the corporate world is moving ground effect into the drone age. At the European Rotors show in Madrid, Levanta Tech finally pulled the curtain back on a physical prototype, moving their project from a collection of renders into the hardware phase. CEO Kelly Eckel introduced the world to the Hatia, a fleet of float and fly drones. Traditional drones have to burn fuel or battery just to stay in the air. Levanta Tech's float and fly philosophy is different. Because the Halia is a ground effect vehicle with a marine stable hull, it can simply land on the water and turn its motors off. It can float indefinitely with low detectability, acting as a persistent sensor node then put back up into the air the moment its mission resumes. Technically, the Halia is a masterclass in modern power-augmented RAM or POW. As we've discussed, getting a wig craft to unstick from the water is the hardest part. Levanta Tech's patented hover foils are the secret. These foils use a Lippish-style inverse delta shape, but they are integrated into a ducted air system. Intakes on top of the fuselage draw air in and blast it directly under these foils. This generates a high pressure bubble that generates immediate buoyancy and reduces drag by nearly 90% during the takeoff run. This gives the Halia genuine stall or short takeoff and landing capabilities, allowing it to break out and reach its 270 km/h cruise speed in a fraction of the distance required by the Navy prototype Met found. Levanta Tech isn't just building one size, they are scaling the physics across 3 distinct classes. They have an S, an M, and an X. The X is a scaled up cargo Titan, and we're talking about a ton-kilogram payload and a 5,000 km range. The mission sets for these crafts are serious. We're talking about persistence ISR, search and rescue, and even kinetic engagement. Renders show the Halia X outfitted with multiple lightweight torpedoes. Because it can loiter on the water with the engine off, it can wait silently for a target, then use its ground effect speed to intercept. You'll also notice the interesting flying wing tied tail, with no distinctive control surfaces or vertical surfaces. From what we can see, it relies on an extremely clean aerodynamic profile. However, this raises immediate red flags for aero engineers. Without visible rudders or traditional elevators, it's unclear how the Halia handles yaw stability or manages the aggressive pitch changes required to maintain that delicate altitude above moving waves. So is this still vaporware? Despite the fancy carbon fiber shell on the show floor, the evidence is shifting towards yes. Levanta Tech says it has validated their computational models through wind tunnel testing at a TRL5 level, and having a physical prototype is a step in the right direction. But here's a reality check. We are well past their projected 2024 testing dates. No footage has been shared showing that this prototype actually performs. In the wig world, hardware doesn't lie, but hardware on a pedestal isn't the same as hardware on the water. There's currently zero evidence that those Lippish pods can actually generate the static pressure needed to break surface tension, or that the ducted fans provide enough lift to get a monster like the Halia X airborne. Until we see spray behind those foils, Levanta Tech remains a beautiful high-tech question mark. While Levanta Tech targets the tactical float and fly drone market, Poseidon Aerospace is playing the big game of global logistics. Headquartered in San Francisco and led by veterans from Amazon's drone program and Lockheed Martin's Skunk Works, Poseidon isn't just building a single craft. Their mission is to drive the price of air freight down to maritime levels, making the delivery of goods across oceans so effortless as a local truck route. But to do that, they've made a technical choice that sets them apart from every other project we've looked at today. Here's the one wingspan above technical distinction. If you look at the Poseidon lineup, particularly the Heron and the Egret, something stands out to the aero enthusiast. The wings are skinny, unlike the broad stubby wings of the Soviet Econoplans or Levantek's Lippish designs. Poseidon has opted for high aspect ratio wings. Technically, the Poseidon fleet are essentially uncrewed seaplanes, not dedicated ground effect vehicles. This is very different engineering philosophy. A dedicated ground effect vehicle is physically pinned to the surface. Its wings are essentially air cushion generators. designed to trap a high pressure volume of air beneath them. Poseidon's skinny wings, however, are designed for aerodynamic efficiency across a range of altitudes. When they are flying one wingspan or less above the water, they do receive a reduction in induced drag. The ground physically blocks the air from spilling over those narrow tips. But they are not surface bound. They are designed to climb, clear weather, and maneuver like traditional aircraft, treating ground effect as a fuel-saving option rather than a physical requirement. Let's look at the fleet, starting with the Seagull. This is their production-ready sea glider and primary tech demonstrator. It's lightweight, battery-powered, autonomous seaplane with a 4 meters wingspan, designed to carry 25 to 50 kilograms of cargo, think medical supplies or emergency electronics, at a speed of 185 kilometers an hour. With an underbody impact shield and a 200 kilometer range, the Seagull is the scout of the fleet, capable of taking off in calm bays and climbing to altitude to bypass coastal terrain or clear rough water that would ground a pure wig. But the real logical heavyweight is the Heron. Currently in development, the Heron is an autonomous amphibious aircraft designed with a 15-meter wingspan. This is where the maths get serious. It's engineered to haul a 2-ton payload. By choosing a seaplane configuration with a high lift wing, Poseidon avoids the extreme longitudinal stability nightmares that James Wamsley and the Navy prototype faced. They're not trying to balance on a razor-thin air cushion. Finally, they have the Egret, the land-based counterpart. With a 15.5 meters wingspan and a range of over 2,700 kilometers, the Egret handles the runway independent logistics over land, complementing the sea-based Heron to create a seamless autonomous network that isn't limited by wave height or sea state. This is a crucial technical advantage for Poseidon. If a Heron encounters a rogue wave or a massive container ship, it doesn't have to stop or hope its AI is fast enough to dodge. It can simply pull back on the yoke and climb to 150 meters, clearing the obstacle with traditional aeronautical safety margins. To power this vision, Poseidon secured an $11 million seed round in late 2024, backed by heavy hitters like Levanta Tech and First Star. Technically, they are solving the global control problem by integrating Starlink connectivity for real-time telemetry and navigation. With Navy and Coast Guard trials planned, their technical bet is clear. The world doesn't need a sea monster strapped on the deck, it needs an uncrewed sea freighter that can deliver cargo to island change like Hawaii for as little as $2 per kilogram. Poseidon is proving that the most efficient way to use the sweet spot might be to use it as an option, not as a cage. They're bridging the gap between the shipyard and the hangar by building a vehicle that understands the air but isn't afraid of the deep. While Poseidon Airspace is betting on the versatility of the uncrewed seaplane, our final project represents the absolute endgame for Ground Effect technology. It carries a name that frankly is a technical PR disaster: Airship. Now I need you to completely erase the image of a slow-moving helium-filled balloon or a Hindenburg-style dirigible from your mind. Technically, the European Airship project has nothing to do with buoyancy. It's an ambitious EU-led consortium, coordinated by the Fraunhofer Gesellschaft, and the acronym actually stands for Autonomous Flying Vehicle for a Sustainable Future. It is a massive fixed-wing autonomous titan. It doesn't use gas to float, it uses raw aerodynamic efficiency to soar mere meters above the water. The technical philosophy here is total human deletion. In the world of heavy lift maritime aerospace, weight is the ultimate enemy. By removing humans, the Airship project clears out thousands of kilograms of non-productive mass. This isn't just about saving fuel, it's about decarbonizing the ocean. Currently, maritime shipping accounts for nearly 3% of global CO2 emissions. Airship's goal is to bridge the massive gap between slow, bunker fuel chugging container ships, which take weeks to cross the ocean, and the incredibly expensive cargo jets we rely on for express delivery. The maths here is compelling. They are aiming for a vehicle that is 3 to 5 times faster than an ocean freighter, but operates at a fraction of the cost of traditional air freight. It's the missing middle of global logistics. The technical secret to the airship's efficiency is that L/D multiplier. When you scale a wing to this size, potentially hundreds of feet across, the ground effect sweet spot becomes a 3 to 5 meter window. By cruising at this altitude, the Airship project aims to crush induced drag to nearly zero. But doing this at high speed, roughly 370 to 560 km per hour, presents a terrifying safety hurdle. To solve this, the Fraunhofer-led team is developing an autonomous marine navigation system. Unlike a plane in the empty sky, a sea skimmer at 370 km per hour is constantly at risk of colliding with rogue waves, whales, and small fishing vessels that don't appear on a standard radar. The Airship project uses advanced sensor fusion, combining high-frequency LiDAR, multispectral cameras, and AI-driven pathfinding to see and dodge obstacles without a human ever touching the controls. Building an autonomous wing the size of a football field that won't flip in a North Atlantic gale is arguably the single hardest engineering challenge in the world today. Is Airship the definite answer to sustainable global trade, or is it a dream that's just too big to fly? One thing is certain, if the Fraunhofer team pulls this off, the ocean will never be the same again. While the Fraunhofer team in Europe and startups in San Francisco are betting on a fully autonomous future, a global aerospace giant is about to turn ground effect into a daily commute. This is the Airfish 8, and technically it is a frontrunner of a very high-stakes race. You've likely seen the sleek Regent Viceroy, the higher-profile US Sea Glider backed by Silicon Valley billions. But while Regent is still navigating its testing cycles and complex foil-to-fly transitions, ST Engineering is currently beating them to the punch. Through their joint venture, ST Engineering AirX, they have officially put a deadline on the future. The Airfish 8 is set for a commercial launch in 2026. This isn't just a prototype, it's the culmination of nearly 40 years of technical evolution, and it's set to become the first ground effect machine in real sustained commercial use. To understand why ST Engineering is winning, you have to look at the Airfish's long and grueling history. Eventually, the technology was acquired by Singapore's WidgetWorks, who spent years perfecting the Airfish 8 platform. By the time ST Engineering stepped in to form AirX, the aerodynamic maths had already been proving through decades of salt spray and real-world trials. Now, here's a major technical update. If you look at the legacy WidgetWorks website, you'll see the Airfish 8 listed as a Type A craft, meaning it's strictly surface-bound. But for the 2026 commercial launch, ST Engineering AirX has shifted the goalposts. They are currently seeking IMO Type B certification. This is a massive technical and operational leap. A Type A craft is physically trapped in the air cushion. It cannot clear a large container ship or a rocky outcrop. But a Type B craft, the version being engineered for the 2026 launch, possesses the structural integrity and control authority to jump out of the ground effect up to an altitude of 150 meters. This allows the pilot to clear obstacles to dodge rough sea states in the crowded Singapore Strait, all while maintaining its legal status as a ship. Technically, ST Engineering's advantage over companies like Regent is mechanical simplicity, while Regent is building a complex, all-electric craft with retractable hydrofoils. The Airfish 8 relies on a standard V8 automotive engine. By using a traditional internal combustion heart, they've sidestepped the massive weight penalties of current battery technology. The Airfish 8 utilizes a Lippisch inverse delta wing, a shape Fisher refined from Alexander Lippisch's original research. This wing is inherently stable. If the nose pitches up, the center of pressure automatically moves to push it back down. It is a physics-based safety net that allows the Airfish to cruise at 90 knots with airplane-level efficiency and boat-level maintenance costs. With a letter of intent already secured from Pelita Air, a major Indonesian carrier, the 2026 launch is targeting the Archipelago Highway between Singapore, Batam, and Bintam. They aim to turn a multi-hour ferry ride into a 45-minute skim. By bypassing the red tape of civil aviation and the multi-billion-dollar costs of airports, ST Engineering has found a legal and technical crowbar to finally pry open the maritime aerospace age. For 100 years, the grand arc of progress in the sky was a race to the stars, a relentless drive to go higher, colder, and faster. But as we move towards 2026, the story is changing. We're looking back down at the deck as we fight for zero-emission logistics and high-efficiency transport. The sweet spot we ignored for decades is becoming the most valuable piece of real estate in airspace. What we've seen today is the convergence of two worlds that used to speak different languages. In the shed at Rudyard Lake, James proved that the basic physics of the boundary layer are accessible to anyone who can master the breakout speed. In Idaho, Matt Spears is performing a technical exorcism, baking 30 years of moisture out of a Navy legend to prove that the hovercraft system is still the effective way to pop a hull out of the water. At the corporate level, the gamble is now a reality. Levanta Tech is taking the Lippisch wing, giving it an autonomous brain, while ST Engineering is taking that same shape, honoring Hanno Fischer's decades of research, giving it a V8 heart for the masses. They are betting that the Archipelago Highway is the proof of concept the world needs to see. Meanwhile, companies like Poseidon Aerospace, like Regent, are proving that the seaplane pivot using high-spec, skinny wings might be the most practical way to bridge the gap between a boat and a plane. And at the absolute peak of the ambition curve, the Fraunhofer-led Airship project is daring to envision a world where the human pilot is deleted entirely, replaced by a transoceanic conveyor belt of hydrogen-powered autonomous wings. The boundary layer between the shipyard and the hangar is officially gone. We are no longer building boats or planes, we are building skim machines. We are finally taming the violent, unpredictable boundary layer between the deep and the sky. So, what is your pick of the future? Would you trust your 2026 commute to the Airfish 8? Let me know your thoughts in the comments below. We read every technical theory and restoration tip you guys leave. For now, thank you very much for watching. Keep in the loop by hitting that subscribe button, and we'll see you here for the next episode of One Wingspan Above. Keep on skimming.